to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today I'm pleased to welcome Simon Whiteley. Simon is an independent system safety engineering consultant and managing director at Whiteley Aerospace Safety Engineering and Management Limited. He's worked as a system safety engineer across the entire product and project lifecycle and with a variety of industries, including civil and defense aerospace, air traffic control, weapons systems, armored automotive, maritime and nuclear defense, healthcare, government IT, pharmaceuticals, and most recently, rail transportation. Simon offers consulting, training, coaching, and support regarding system safety engineering and safety critical project management. He received his bachelor's degree in aerospace engineering with honors from the University of Lincoln and a master's degree in safety critical systems engineering from the University of York. Simon Whiteley, welcome, and thanks for joining us.
Hi, Tim. Thanks for the warm welcome. I really appreciate it.
So, Simon, in our earlier conversation, we were talking about applying systems theory to safety engineering, which is becoming known by some people by the acronym STAMP, or Systems Theoretic Accident Model and Processes. Can you tell our listeners a little more about this idea? And specifically, how is this different from traditional root cause analysis and reliability theory?
Yeah, sure, Tim, of course. So STAMP, as you mentioned, is an acronym, and that acronym refers to two main things, really, two main components. The first is an accident causality model, which is based upon systems theory and control theory. So that introduces the concepts of components and interactions, structure, hierarchy, emergent properties, and of course, control feedback loops. And it changes the emphasis from preventing failures to enforcing constraints on system behavior and interactions among system components. And that introduces the concepts of safety constraints and hierarchical control structures. Now, where this is slightly different to more traditional safety and reliability is that it includes the focus of traditional safety and reliability, so looking at failures and preventing failures, but it changes the emphasis and changes the way accidents are envisaged from simple management of failures to dynamic control. So thinking about a system as a dynamic control challenge and dealing with accidents in terms of dynamic control. And it does this through a number of processes. So currently there are 4 processes that can be used at different parts of the system lifecycle. So there's a hazard analysis process known as STPA, which stands for Systems Theoretic Process Analysis. There is an accident or incident analysis called CAST, which stands for Causal Analysis based on Systems Theory. There is also a cybersecurity version of STPA, which deals with cybersecurity challenges called STPA-SEC. And then there's a concept analysis approach called STECA, or STECA, which stands for Systems Theoretic Early Concept Analysis. And all of those those approaches are based on systems theory and control theory, and they go beyond traditional reliability focus assessments to look at more than just failures. And that sort of encompasses new types of accidents where, strictly speaking, no failure has occurred, the system has behaved as designed. And a prime example of that is the recent Uber accident that killed a pedestrian. The vehicle appeared to behave as it was designed to behave. So strictly, there was no failure, but obviously that situation was dangerous and somebody unfortunately lost their life.
Yeah, obviously it was a failure of the system as a whole, even though it may have worked as designed. As we're recording this story has just come out, just reported today in the Wall Street Journal. I know the accident occurred some time ago, but I guess they're finally getting closer to understanding the causes. But it is an interesting and very timely example.
Absolutely. I think being totally honest about it, I think it's a watershed moment, not just in the terms of autonomous vehicles, but also in safety guided design.
Yeah, I know. Again, this is very timely, but I wonder if you have any initial thoughts about what's going on with autonomous vehicles. Generally speaking, how can STAMP be used to help design a safer system for self-driving cars and other kinds of vehicles?
Well, it can be used in two prime areas. The first, most obvious, is in accident investigation. If the NTSB or anybody else interested or involved in investigations was to use the CAST accident analysis approach, they will be able to identify more causes of accidents much more quickly than traditional investigation analysis approaches. Now, from a vehicle design and particularly from a concept perspective, as I mentioned, you could employ STECA or STPA, and that would allow you to, even before you decide on what technologies you're going to use as part of your autonomous vehicles, what sensors, whether it's radar or LiDAR, et cetera, you could use those methods to identify the high-level safety constraints that the vehicle and its systems must fulfill. And then as you go through the design process and iterate the design and make it more detailed, you can use the STPA process to help drive out the important safety constraints that need to be enforced by the design. So, things like sensor performance or computer software control algorithms. So in the case of, we mentioned the Uber accident, some of the high-level safety constraints to do with sensor behavior and the behavior of the software, in the control software, in terms of interpreting that potential threat on the road and then taking appropriate action. But not just applied to technology. The stamp-based approach can also look at the social technical system. So that includes the driver, the human factors of that, even up the hierarchical control structure to consider the management of the vehicle trials, and even down to the selection of safety drivers. So it can be quite all-encompassing. But if you sort of take an abstract step back from that, the vehicle regulators could actually employ this approach to define the requirements that organizations such as Uber or Tesla should actually perform as part of their safety processes and even their trials acceptance processes.
Yeah, one of the things that seems interesting to me about STAMP is again the emphasis on control systems, not just not just how things perform, but whether there are effective controls in place. Really looking at the entire system, as you mentioned.
Absolutely, it's a systems-based approach which looks at the entire system, not just the technology. So as I used the term earlier on, social technical system, that term implies technology, people, organizations, hierarchy, all the way up to governments and regulators and lawmakers.
Interesting. I know from my own experience that one of the biggest issues that system designers have to deal with are low probability but high impact events. These are, I think we consistently talk ourselves into the probability being much lower than it actually is, because we're hoping that this just isn't going to be a problem. Is there a way that STAMP can help designers evaluate these kinds of events?
Absolutely, but it's a bit of a double-edged sword. So as you sort of recognize and highlight, that there is often an emphasis on trying to work with the numbers and trying to assess or guess that the numbers will be low and try and justify that. One of the sort of double-edged sword with the stamp-based approaches is they don't encompass any kind of probabilistic analysis. It is all a worst-case analysis, and it basically highlights all of the scenarios, all of the causal scenarios that could lead to an accident. So you know that they exist, and then it's up to the system designer to essentially do something about those potential causal scenarios. And if the system designer decides for whatever justified reason that they don't want to deal with that particular causal scenario, then at least they can document the justification and be explicit about it instead of being implicit and not being certain that they've captured everything. So for me, that's one of the real massive advantages of these approaches. But as I say, it's a bit of a double-edged sword because it makes things explicit that perhaps in the past people may not want to make explicit or may not want to acknowledge is an issue that then needs dealing with.
Yeah, I mean, I think of FMEA. There are a lot of situations where we give something a low RPN score because we decide that it's low probability, or the level of the ability to detect is very low, or something like that. So, when we prioritize after an FMEA analysis, we say, well, yeah, that could happen, but we're just not going to take any action. But it sounds like STAMP tries to deal with these things more explicitly.
Absolutely, yes. So once well, take it, for example, you mentioned there about detection. In the STAMP control structure model that you create as part of any STAMP analysis, because it is a model-based technique, as part of that model, you actually model the control loop, the feedback loop. And so it makes, as part of doing the analysis, you make explicit what that control feedback loop might be and whether it can actually detect the particular issue that you're concerned about. And obviously, if the feedback loop is not present or is missing, or if there is a problem with the feedback, then as part of that analysis, it becomes explicit, and then you can make design decisions as to how and whether you're going to deal with that.
Simon, I know you've worked with a lot of different systems, but I wonder if you could give us a specific example of how STAMP has been used to create a safer system.
Absolutely. It's a bit of a challenge, really, because STAMP its use is still very much in the academic arena. And myself and a number of others are trying our best to try and move it out of the academic arena into the mainstream. Because, I mean, as you've seen, I've been around and done quite a lot of interesting work on different systems and had challenges with fault trees and event trees and FMEAs and HAZOPs and all of those analyses. And I can see that this approach will deal with a lot of the limitations and challenges with those approaches and give us a more competitive advantage in identifying and dealing with other causes of accidents over and above failures. Now, that means that as part of my work with various clients and organizations, naturally they work already to industry standards that don't require STAMP analysis to be done because it's not a recognized standard. So I've had to use it sort of under the radar, back of the fact packet sort of thing. So I've used it to sort of either help me win an argument, for want of a better word, in a safety analysis meeting, to sort of emphasize a safety scenario that doesn't necessarily come out of a fault tree analysis, for example, or a bow tie analysis, or there are hints that that scenario exists. But because it's not explicit enough to sort of win the discussion amongst a team of people trying to identify hazards, it was always a challenge. And so as part of creating the control structure model, the first step of any STAMP-based analysis, I was able to identify some interesting interactions in the air traffic control domain. So without sort of getting too specific, there was a project to change some separation distances over the North Atlantic. And as part of that analysis, it was constrained to the air traffic control part of the system. And obviously the air traffic controllers, they receive information from onboard aircraft avionics boxes that give them information about the equipment state and location of the aircraft. And as part of that analysis using bow ties, I suspected there were a few scenarios to do with the behavior and serviceability of the avionics equipment on board the aircraft. But because that was effectively outside of the normal boundary of the air traffic control analysis, it didn't sort of meaningfully fit into the bow tie analysis that was being done. And so by drawing the control structure model, I was able to show a picture of how the aircraft and its equipment interacted with the air traffic control equipment and how important safety constraints on the behavior of the aircraft was necessary for ensuring safety. And so whilst it wasn't an air traffic control system safety constraint, it was important that those constraints were met to ensure safety of the entire air traffic control system. And so it prompted a few actions to go and talk to the aircraft operators that were taking part in the trial and help to inform the procedures that the aircrew would use.
And the air traffic controllers themselves, I would assume, right? They're part of this system too.
Absolutely. So they had their procedures, which from this couple of subtle scenarios I identified, it didn't ultimately change their behaviour, but it certainly made them aware of the context of the aircrew and their behaviour.
I think that's one of the things that's really kind of appealing to me about STAMP, or a systems approach, is that it looks at humans, who are in many systems one of the biggest causes of reliability risk.
Absolutely, and that's something I maybe should have emphasised in the first place. So STAMP, the way STAMP works, because of the modelling aspect of it, it allows you to model not just the technology, and the hardware and software. It allows you to think about the humans that are directly involved in the operation of a system, but also the management of those people and the technology, the design organizations, the operations organizations, even if you want to go far enough, even to consider the emergency response organizations and the design and constraints that are necessary across all of those different stakeholders. But one of the challenges I've found with teaching the approach and applying it is because the traditional approach and typically the standards and regulations for a particular industry, they very much focus on the humans, and particularly in civil aerospace, the regulations and the requirements almost explicitly exclude the aircrew. So it's all about reliability of hardware and software without necessarily appreciating the contribution from humans who, like I said earlier on, this is more than just failures. If humans behave as humans, not recognizing that everyone turns up to work to kill people or do a bad job, we have to consider that in the design of our systems. And the STAMP approach enables you to do that explicitly, specifically to the point, if you want to go that far, to designing the procedures, designing their training, even down to designing their work schedule to avoid fatigue.
Good point. Very good point. Simon, you've worked in a lot of different kinds of businesses and industries that have very high standards for safety and reliability. I'm thinking about the aerospace and defense industries. I wonder if you could comment on how STAMP might have value for other kinds of industries that might not have the same high standard for success or safety.
Absolutely. Well, the thing is, STAMP is essentially standards and technology agnostic. So strictly speaking, you can apply it to any system, social technical system of any kind, any mission, if you like. So I know it has come from the application of this approach to safety. So it's very much out of focusing on safety, but you could apply it to mission assurance, cybersecurity, even business if you wanted to go that far. But from industries that are perhaps less mature than aerospace and defense, applying the STAMP-based approach, fundamentally, it allows you to identify causal scenarios that then you can either design out or decide to deal with in a more robust way. You don't necessarily need to conform with a particular safety standard because the principles are so sort of straightforward. It's essentially build a control structure model of the system that you're interested in, identify unsafe control actions, as they're called, or interactions amongst the components in that structure. And then once you've done that, identify causal scenarios that lead to those unsafe control actions. And all of that is essentially agnostic to what you apply it to. So whether it's aerospace or autonomous vehicles or even public water supplies.
Just coming back to the autonomous vehicles for a minute, yes. Simon, this reminds me of, I remember hearing a story about the early days of elevators when driverless elevators were first introduced. People, elevators that did not have a human on board who seemed to be operating the elevator. There were people that were reluctant to get in the elevator because they couldn't understand who was driving. And there was a lot of skepticism. It really does seem like autonomous vehicles are coming. They're here. Do you have any insight, any comment about how you see this evolving over the next few years?
I do, but it might not be a popular opinion. To compare elevators to autonomous cars, there's one really important distinction which a lot of the media don't tend to recognise, because a lot of the media commentators are not engineers like you or I, and that the prime difference is the level of complexity of the system and the environment that system operates in. So an elevator in an office building, I'm talking about a traditional elevator that goes up and down, not these magical ones that go horizontally as well. I'll put those to one side. But a traditional elevator, they're quite simple. They're not that complex. The system states are well defined, well understood. And apart from maybe an asteroid or a meteorite or a building fire, the environment is quite predictable and can be designed for, and is under the control of the building operator or the lift provider, the operator.
And they stay on track.
Yeah, so they're designed to stay on track as much as possible. Whereas when we're talking about autonomous vehicles, not only is the vehicle itself in a very dynamic, very unpredictable environment in most situations, it also can rapidly evolve into a totally unprecedented situation. And so first off, the environment that the vehicle operates in is immensely complex. It's very dynamic, it's unpredictable, and pretty much anything can happen. I mean, anything from a child running out in the road to an aeroplane or helicopter crash landing on the road in front of you.
Good point.
So straight off, the complexity of the environment is different. Then we look at the complexity of the task of not only driving a vehicle in all of that complex environment, but also the level and type of sensors that are necessary to cover the entire driving range. So if you're driving in a constrained city grid that is not very complex, that is entirely different to operating on the German autobahns at 150 miles an hour, for example. And so system designers have to necessarily constrain the operational envelope of that vehicle so that they can design for it and hopefully design for safety of it. But because of the complexity of some of these systems and the environment that they're in, the type of safety analysis that needs to be done, the type of reliability analysis that needs to be done, becomes more susceptible to human error in the design, analysis and requirements setting. And so in the case of this recent Uber accident, it appears that they've missed some quite important functional safety and system safety requirements that, had they used, in this case, the stamp-based analysis, I'm confident they would have picked those things up and mitigated against them. So in terms of the future, I think they are going to come. I think there's going to be more accidents and more deaths. Unfortunately, there are no regulations that I'm aware of that stipulate the level of data recording and information collection that's necessary to demonstrate whether it was the driver that was at fault or whether it was the autonomous vehicle's fault that an accident occurred. And I think there's going to be a lot of legal battles with manufacturers to establish fault. The spectre of cybersecurity is also very significant, because if you give a vehicle a connection to the internet and the ability to control its speed and direction, it's ripe for abuse. But because of the nature of these systems, there would be no evidence that tampering has taken place. And I know that sounds like a really dark and horrible picture painted, but I am a safety engineer. I am cynical, and if I ever see a Tesla or a Volvo or any of these other highly automated cars on the road, I do tend to keep my distance.
I don't blame you. It's part of your occupational training.
It is. I'm cynical, and my hair's going white.
Well, I've always said it doesn't really matter what color the hair is, as long as we have hair, right?
Absolutely. Well, as much as I have, some of it's falling out.
Simon, this has been great. Thanks so much for joining us today.
No, thank you. I really enjoy it, and I really hope the listeners enjoyed that as well.
That was Simon Whiteley, System Safety Engineering Consultant and Managing Director at Whiteley Aerospace Safety Engineering and Management Limited. For more information, please visit www.whiteleysafety.co.uk. That's WHITLEY-SAFETY.co.uk. And for more information about STAMP, we'll post Simon's YouTube video in the notes for this recording. This is Tim Rogers. Thanks for joining us.